All right, so now we're going to talk about affine and dual affine coordinate systems. Okay, and the reason why we study it's like these affine and dual affine coordinate systems is based on sort of the observation that this notion of convexity is not coordinate independent, right? So, so you observe that when a function psi of theta, for example, is convex in a coordinate system, theta, right? The same function expressed in a different coordinate system is not necessarily convex in the new coordinates. Right, is not necessarily convex as a function of the other coordinate system. Okay, and one way to sort of see this is that, you know, it's like when we think about convexity, be it convex objects or convex functions, right? There's this idea that you're comparing, you know, it's like the function value. It's like of a function, it's like with its linear interpolant along something which is analogous to a straight line. But the bottom line, if you will, is that this notion of a straight line, absent any additional geometric structure, right, is really defined, it's like by our choice of coordinate systems. So it's not so surprising, if you will, that convexity then isn't a well-defined property, which is intrinsic, if you will. It's like to you know, it's like to the space you're working with and the function, if you will. Okay, so, but it doesn't lead then to the following question. Okay, so if you can't allow all possible changes of coordinates, are there specific classes of coordinate changes which would preserve this notion of convexity? Okay, so, so the point is that the notion of convexity sort of is invariant with respect to not all possible transformations, but to affine transformations. Okay, and what do I mean by an affine transformation? I mean that I have something which depends linearly on the coordinates plus some constant displacement. Right, so where A is a non-singular constant matrix and B is a constant vector. Okay, and you can convince yourself that under this notion of affine transformation, straight lines remain straight. And so that's sort of, again, it's consistent with this kind of intuitive sense which we have, that one of the problems, if you will, right, in allowing yourself the flexibility to change coordinates in a fully arbitrary way is that it doesn't preserve the notion of straightness of lines. Okay, but under affine transformations, something which is straight in the original coordinate system remains straight in some very natural way. It's like in the new coordinate system. Okay, so now we want to fix some sort of coordinate system. It's like in which this function is convex, right? So now, right, we fix the coordinate system. Let's call it theta, in which phi of theta is convex. And then we introduce sort of geometric structures. It's like on M. Sort of based on it. Okay. So, so we consider this theta as an affine coordinate system. And what happens when we do that is it endows the manifold on which we've put this coordinate system on with an affine flat structure. Okay. So what that means is that M is a flat manifold with respect to this sort of geometric structure. And, you know, it's like the coordinate lines of the coordinate system are straight lines. Right, so M is a flat manifold. And the coordinate axes are straight lines. Okay, and then more generally, it's like we can try to characterize as like what are straight lines. It's like in this space, right? Any curve, sort of theta of t in M of the form theta of t is equal to a of t plus b is a straight line. Where sort of a and b are constant vectors. Okay, so this is, you know, exactly what you would expect from the usual intuition you have. It's like about Euclidean spaces, right? And then we refer to these lines, it's like as, or curves as geodesics, right? We refer to such curves as geodesics. Of an affine manifold. And let me sort of just be clear, it's like if you recall, it's like that when we talk about geodesics as generalizations of straight lines, right? Straight lines in Euclidean spaces have two properties. One of which is that they're the shortest line segment connecting 2 points, and the other which is that they are lines, it's like which don't change direction, right? So, and so you can ask yourself when we say that these lines are geodesics, what notion of straight do we refer to? Okay, so I should say that in this context, right, geodesics do not mean the shortest path connecting two points. But one where the curve keeps pointing in the same direction, whatever that means. Okay. All right. So this notion of geodesic is invariant under affine transformations. So the geodesic here is, well, I should say that the geodesic of an affine manifold, right? Right, is invariant or maybe I should say that the notion of a geodesic geodesics is invariant under affine transformations. Which is another way of saying that if you have a curve of this form and you apply an affine transformation to that, it is still a curve of this kind of general form in the new coordinate system, right? Okay. So, all right. So now we have some coordinate system. You can ask yourself, well, what happens if you look at the dual coordinate system, right? So, as before, we can consider the dual coordinates. Theta star, which are given by the Legendre transform. Theta star is equal to the gradient of psi theta. And consider it as a new set of affine coordinates. And with this new affine coordinate system, you have another affine structure and another notion of geodesics, right? Okay. So this gives two notions of geodesics and flatness. Okay. So these are two different geometric structures, if you will, on the same manifold. Okay. And we say that a manifold endowed with this is with these structures, these sort of dual structures, are dually flat. And the coordinate systems, as we sort of alluded to, are related by the Legendre transform. Sort of the two flat coordinates are related by the Legendre transform. Right. So theta star is equal to gradient of psi theta. Right. So anyway, so that's the point, right? That when you endow a manifold, it's like with a coordinate system. It's like you can, it's like use that to define some notion of straight lines. It's like or geodesics. And then if, it's like in one of those coordinate systems, it's like you have then a convex function, then you can look at its Legendre dual, right? And use that to define a dual coordinate system. And on that dual coordinate system, you can also, it's like naturally induce some notion of straight lines. And the observation in general is that those two notions may not agree with each other. So something which is a geodesic, it's like in one coordinate system, may not be a geodesic in the other coordinate system. Okay, so and what happens basically is that depending on the problem, right, certain objects of interest, it's like maybe geodesics in one versus, but not in the other representation or not in the other structure. And so, being sort of selective about whether you choose the prime or dual representation is helpful. It's like in making the computations easier, for example, right? So you'll see it's like again and again, it's like as we go through this quarter, that, it's like being selective, it's like in whether you work in the prime or dual representation as the situation, it's like warrants, right, will allow you to, take advantage of this kind of dually flat structure in order to make certain computations much more tractable. So let me just stop here for now.